In this final lesson in the background information series, we want to talk about impedance. This is a pretty complex topic, and we're just going to hit the highlights here. I do cover this in much more detail in my book, PCB Currents, but I'm going to just highlight a couple of things in this lesson as a way of background information for the rest of what's going to follow. We have three primary passive components in electronics: inductors, resistors, and capacitors. And we can think of these three primary passive components as being part of a single spectrum. An inductor has an impedance at DC of 0. It has an impedance at very high frequency that approaches infinity, and it's got a voltage phase shift of 90 degrees. A capacitor has an impedance at DC that approaches infinity. It's got an impedance at very high frequency that approaches 0, and it's got a voltage phase shift of minus 90 degrees. The resistor occupies a special spot or a special case right smack dab in the middle. It's got an impedance at DC of whatever the resistive value is. It's got an impedance at very high frequency that is the same value. That is, the value of a resistor doesn't change with frequency. And it's got a voltage phase shift of 0. Now, throughout this lesson, we're going to treat these three components as if they are pure. A pure inductor, pure resistor, and pure capacitor. And here's what we mean by phase shift. Here is, say, the voltage waveform across a resistor. Here is the current waveform through the same resistor. And they are in phase. They peak at the same time. They have the same trough. They have the same shape. The only difference between them is a scale factor. We're looking at Ohm's law here. The scale factor is R, the value of resistance. If the value of the resistance were 1, then these two curves would look exactly the same. Reactive phase shift is 90 degrees. Reactive phase shift is what we get with inductors and capacitors. If the red curve is voltage and the black curve is current, then for an inductor, the voltage curve is peaking 90 degrees before the current curve does. So voltage leads current by 90 degrees. For a capacitor, the voltage curve lags the current curve by 90 degrees. It peaks 90 degrees later. Its trough is 90 degrees later. It crosses the axis 90 degrees later. If we look at these three curves together, the voltage curve for the inductor peaks 90 degrees ahead of current. The voltage curve for the capacitor peaks 90 degrees after the current. The voltage curve for the resistor peaks at exactly the same time as the current. The voltage across the inductor and the voltage across the capacitor are exactly 180 degrees out of phase. And one of the things that is sometimes difficult for engineers to grasp early in their education is that this relationship never changes. This is a fixed relationship. The voltage phase shift for an inductor is always 90 degrees. It is never anything else. The voltage phase shift for a capacitor is always minus 90 degrees. It is never anything else. The voltage phase relationship between an inductor and a capacitor is always 180 degrees, and it is never anything else. The only time that we can get a phase shift different from 0 or plus or minus 90 degrees is when we start combining components. Now, if we bring an LC circuit into this relationship that we looked at a couple of minutes ago, whether it's a series LC circuit or a parallel LC circuit, what we add here is that the impedance at DC of an LC circuit is either 0 or infinity, depending on whether we're talking about a parallel or a series LC circuit. The impedance at very high frequencies is either 0 or infinity, depending on whether we're talking about a parallel or a series LC circuit. And the voltage phase shift for an LC circuit is either plus 90 degrees or minus 90 degrees, or in a very special case, 0 degrees at a very special point we call the resonant point. Now here's an impedance curve for a resistor. We have frequency on this axis, we have impedance on this axis. We typically plot these axes using a logarithmic scale because we want to cover a very large range. And the resistance curve is horizontal when we do this. Any impedance curve that is horizontal over part of its range is resistive over that range. The impedance or the reactance of an inductor is given by this expression. The reactance is omega L, or remember that omega is equal to 2 pi f. It's equal to 2 pi f times L. And when we plot that on an impedance curve, the impedance of an inductor is what we call upward sloping to the right. It is low at lower frequencies. It is high at higher frequencies. Any impedance curve that is upward sloping to the right is inductive over that range. And the voltage across an inductance is given by this expression, L times the change in current divided by the change in time. Looking at that relationship in a little more detail, the voltage across an inductor is given by L times di dt. That's the calculus term. If you don't like calculus, well, then we can express it this way. It's the inductance times the change in current over the change in time. We can interpret the change in time as the rise time, the change in current as being the switched current. So if we put in a typical relationship, let the inductance be 10 nanohenries, which is 10 to the minus 8th. Let the rise time be 1/10 of a nanosecond, or 100 picoseconds, or 10 to the minus 10th. Plug it into this relationship, then we can find that the voltage is 100 times the change in current. That seems like a lot. And it can be a lot, but the reason is because the rise time is so short. If we were dealing with rise times that were a millisecond, well, then this wouldn't be very big at all. But when the rise time is 100 picoseconds, well, all of a sudden we can get some very sharp voltage spikes across an inductor. Now, the impedance or the reactance of a capacitor is given by the expression X, the reactance, is minus 1 over omega C, or minus 1 over 2 pi f C. The minus sign does not mean minus impedance. It means a minus phase shift, or a minus 90 degree phase shift. If we plot the reactance or the impedance of a capacitor, that is what we call downward sloping to the right. It's very high at low frequencies. It's very low at high frequencies. Any impedance curve that is downward sloping to the right is capacitive over that range. Now, if we want to look at the impedance or the reactance of an LC circuit, it starts getting a little bit more complicated, but we simply just sum the terms. If we have a series circuit, well, the reactance is the sum of the reactance of the inductor plus the reactance of the capacitor. If we're looking at a parallel LC circuit, well, it's the parallel combination formula, which works out to this. If we look at setting these terms to 0, set this term to 0 right there, or set this denominator to 0, which is this expression right here, set to 0, either one of these two cases is satisfied when omega equals 1 over the square root of L times C. And remember that omega equals 2 pi f. When that happens, this goes to 0, or this denominator goes to 0. That is the point that we call the resonant point. If we look at a series LC circuit, here is the reactance of the capacitor, downward sloping to the right. Here is the reactance of the inductor, upward sloping to the right. This LC circuit is mostly capacitive at lower frequencies. It is mostly inductive at higher frequencies. But if we get right around the point where the reactances are the same, the two reactances interact and the impedance actually goes to zero. And it goes to zero at that special resonant point. And we don't mean just really low. We mean truly zero. If we look at a parallel LC circuit, well, here again is the reactance of the inductance curve. Here's the reactance of the capacitance curve. And at the point where they start getting very close together, they start interacting and the impedance goes up to infinity. And we don't mean the impedance gets really high. We mean the impedance goes all the way to infinity. That is at the special point of resonance. And here's what actually happens. If we could inject a current into this circuit at the exact resonant frequency, what would happen is that current would begin to circulate back and forth in this loop and would never come back out again. That's why the impedance looks so high. If we injected a current in here, it would never come back out the other side. It would get trapped in here and just go back and forth. These are ideal components. There's no resistance, so there's no loss. And so this would continue on forever. The current would never be able to escape for that particular frequency. Now in real life, there would be some losses in here and the circuit would eventually die out. But nevertheless, resonance has some very interesting points that we can use for, say, tuning a circuit, tuning a radio, tuning an oscillator, and so on. If we combine two parallel LC circuits, well, the first LC circuit looks like this. That's the one labeled 1. The second one looks like this. That's the circuit labeled 2. But then there's a parallel LC resonance that occurs halfway between. That's when this inductor and this capacitor work together to form a parallel LC circuit. So when we have two parallel LC circuits like this together, we can get what's called an anti-resonant or a parallel resonant point in between the individual resonant points of the two circuits by themselves. Where do we see this? Bypass capacitors. Now, if we look at the general case of impedance, where we have a resistor and an inductor and a capacitor, well, the impedance at DC can be any value between 0 and infinity. The impedance at a very high frequency can be any value between 0 and infinity. And the voltage phase shift can be any value between minus 90 degrees and plus 90 degrees. Impedance is where we get any value and any range anywhere. If we're just talking about inductors, resistors, and capacitors, we're constrained to certain kinds of relationships. But when we get to impedance, all the constraints are off and we can have any value anywhere. And this is where it starts getting pretty complicated. The general meaning of impedance is this. Resistance, R, is what we get with resistance. Reactance, X, is what we get with inductance and capacitance. And we showed the two formulas for the reactance of an inductor and the reactance of a capacitor. Impedance is what we get when we combine them. And the combination looks like this. Impedance is resistance plus J times reactance, where J is the square root of minus 1. There is a point in Electrical Engineering 101 when an instructor or a professor goes through a derivation and he ends up at this point and says that the impedance is resistance plus this times the square root of minus 1. And then typically there's this pregnant pause where the instructor stops and waits for that to sink in, because for many students that's the first time they ever see the expression the square root of minus 1, which we call an imaginary number because the square root of minus 1 does not exist. There is no number that you can multiply by itself and get minus 1. So this opens up a whole new area of algebra called complex algebra, dealing with imaginary numbers. And it can sound like it's really complicated. But it's not when you grasp the fact that J simply means vertical axis. J simply means 90-degree phase shift. So Z is equal to R plus X, where X is on the vertical axis and R is on the horizontal axis. So when we graph this, here's a graph, here's X. That's the reactance for an inductance or a capacitor. Here's R, the resistance of a resistor. The impedance then becomes this vector, which has a length and it has an angle. The algebra for that we learned back in high school, I hope, where this vector is simply given by the square root of r squared plus x squared. This angle is the angle whose tangent is x over r. It's this side over this side. So the phase angle is the angle whose tangent is x over r. And that then is how we start calculating the parameters for impedance. Any value on the horizontal axis is purely resistive with a phase shift of 0 degrees. Any value on the vertical axis is purely reactive, L or C, with a phase shift of either plus 90 degrees or minus 90 degrees, unless it happens to be the specific point at the origin, in which case the phase shift would be 0 degrees. Any value anywhere else is an impedance with a phase shift that can be any value. Now, let me make 2 points here. One about power dissipation. But before I do that, we talk about impedance. We also talk about resistance. It is not wrong to refer to resistance as impedance. It's not wrong to refer to reactance as impedance. But impedance is, strictly speaking, the sum of the resistance and the reactance multiplied by J, or plotted on the vertical axis. Now, when we talk about power dissipation, power is only dissipated in or lost in the real resistive term. We tend to call this the real part of the impedance expression. We call this the imaginary part of the impedance expression because it's multiplied by the imaginary operator, the square root of minus 1. So power is only dissipated in the real part of the impedance equation, and it's given by the I squared R loss. Power is not dissipated, or power is not lost in the imaginary or the reactive term. Any energy that goes into a capacitor is returned back to the circuit. Any energy that is dissipated in an inductor goes into the magnetic field around the inductor. When the current goes away, that magnetic field collapses and that energy is returned back to the circuit. So the only energy that is lost in a circuit is lost to the real term in the impedance function. And the power that is dissipated or lost is given by the familiar expression I squared R. So where are we going to see this stuff in this course? Well, bypass capacitor self-resonant frequencies, bypass capacitor anti-resonant or parallel resonant points when we combine two or more bypass capacitors in a circuit. Bypass capacitor ESR, when we have a bypass capacitor that is a capacitor that has some lead and pad inductance and has some equivalent series resistance, all of a sudden becomes a little impedance circuit. So bypass capacitor ESR is going to play an important role, we will find. Controlled impedance traces, differential impedance, and trace terminations, especially when we get to lossy transmission lines. All of these places in the coming lessons, we will see some of the stuff we've been discussing in this lesson. So the takeaways from lesson 1.6: inductors, resistors, and capacitors occupy a spectrum, with resistors occupying a special place right in the center. Voltage phase shifts for inductors, resistors, and capacitors are always plus 90, 0, and minus 90 degrees, respectively, with no exceptions. Resistance is what we get with resistors. It's not wrong to call it impedance. Reactance is what we get with inductors and capacitors. It's not wrong to call it impedance. And impedance is what we get when we combine resistance and reactance. Impedance is R plus JX, where J is the square root of -1 and simply means 90 degrees phase shift or vertical axis.
Looking to advance your career by acquiring new skills? Tired of expensive off-site training programs? Wish you could learn from the best instructors in the industry? Look no further than Live Lessons. Self-paced, personal video instruction by the world's leading technology publishers. Each live lesson comes with a DVD featuring 3 to 4 hours of instructor-led classroom training, sample program code that allows you to work along with your personal instructor, and an example-rich study guide. Live lessons allow you to watch the entire course from start to finish, or navigate directly to any of the individual lessons. You'll literally watch over the shoulder of your instructor as he shows you how to build state-of-the-art applications. Live Lessons, the power of the world's leading technology experts at your fingertips. To learn more, visit mylivelessons.com today.